So we have these three different components, these three different field components present. These are effectively three different arms of the same board, each with its own specific shape. And we had seen that if I consider Ex, this was a function of y and z. In y direction, the amplitude was varying, and in z direction, this was propagating. And we had seen that the solution was of the form of sine m pi by a y e minus gamma z. And for omega greater than omega c, we've seen gamma was equal to j beta. Only the propagating term was existing. So we had a sine m pi by a y e minus j beta z. If you notice now, the sine function can be written in exponential forms too. Or phasor form. Remember, I can write, if I have an angle theta, E plus j theta minus of E minus j theta is equal to 2j sine theta. So I can write sine theta of any angle of any argument theta. I can write this as 1 by 2j e plus j theta minus of e minus j theta. And j is nothing but ej pi by 2. So j is ej pi by 2. So I can write 1 by j as e minus j pi by 2. So I can write any angle sine theta as 1 by 2 e minus j pi by 2 ej theta minus of e minus j theta. So if I take the amplitude, if I take the mode amplitude Ex, Y, Z, this would be, we have said, is a sine of m pi by a y e minus j beta z. I can write this now term as a by 2 e j m pi by a y e minus j pi by 2 minus of e minus j m pi by a y e plus j pi by 2 e minus j beta z. Bringing the term inside and combining all the exponential forms, you see something very surprising show up. You end up getting e j m pi by a y minus beta z minus pi by 2 minus of e minus j m pi by a y plus beta z plus pi by 2. This expression, if you look at each of these expressions, this is nothing but the amplitude. A by 2 is nothing but the amplitude. and it's telling me that the amplitude is not changing in XY plane at all. And if you notice this part here, this part is nothing but again a propagating term. It is of the form of some E, J, uh, K, R. This term here is again a very simply a propagating term. And similarly, the second term here is also a propagating term. But the direction has changed a bit. Over here, this part is nothing but some phase difference. Pi by 2 and minus pi by 2 is just phase difference. Over here, I have an argument of y and minus z. Over here, I have an argument of y and plus z. So it's telling me one term in one case as it's not, this term is not moving in z direction, this term is moving in some yz plane. And it's telling me that the amplitude of this term doesn't change in that plane at all. That amplitude part remains like a plane wave, but the plane wave is not traveling in the z direction. The plane wave is traveling in some oblique direction in yz plane. And if the plane wave is, in this case, is going up, then the second term, the plane wave is going down, but with very similar angles. So I'm going to plot this, and plotting it in the yz plane. This is the z direction, the y direction. What it looks like is that there is a term which is the first term a by 2, the first term over here, a by 2, this particular term. This term is not moving in z direction. This term, as it is moving in z direction, is also moving in y direction. So it's making some angle in the yz plane. So I have as if a ray going at some angle. It hits the interface, it hits the metal boundary, and it gets reflected back. It comes down, and similarly it goes up on that side. It makes some angle, we call that angle theta m, to the yz plane, but within this plane, within this region, the magnitude of the field remains the same. So it looks like there is a plane wave which is going up and then getting reflected back from the top, coming and hitting the bottom, getting reflected back, and so forth and so on, as if there are multiple reflections happening to the electromagnetic wave during this period. But it's not just this one single term. When that is happening, you also have another wave which is going in the opposite direction. Remember again, if one is y and minus z, the other is y plus z, which basically means that if one is going upwards, and that whether it is going upwards or downwards would depend on the values of y and z, depend on where the reflection happens. So what this basically is saying is that as I am going up and down, if this plane wave is going up, this plane wave at that point is going opposite direction, but the angle, the tan theta angle, would still remain the same between them. I have another wave which is being reflected in the bottom, and it has an amplitude of a by 2, which is remaining constant as it goes through. Now for this plane wave to exist and remain a plane wave, what has to happen is, so over here I have I have a term like that, and then when it turns around, I still have to have a plane wave. So there has to be a certain phase which has to be met, otherwise the plane wave approximation would be broken. And because of that phase which has to be met, we get discretized solutions. Only certain angles would support that the phase is maintained, that when the reflection happens, it maintains the phase and thus it maintains the plane wave approximation, the plane wave nature of the wave. Only certain angles would allow that, and thus we start seeing discretization of the modes. The discretization of modes occur so that the phase is maintained upon reflections. If the is maintained upon the reflections, and only certain angles allow that. And what happens is, if I have the various modes, for example, for TE1 mode, you're going to see a reflection which is going to be at a much lower angle or a larger angle over here. When I go to TE1 mode or TE2 mode, this angle is going to become smaller for the same frequency. When I go to TE3 mode, this angle is going to become even more acute. And I'm going to see a lot more of these bounces which are going to happen within the waveguide. This is called the ray approximation of modes. It works pretty well for metallic waveguides. You almost get the exact answer you would get if you want to do the full maths. You'll get the exact answers you'll get uh, with exact answers you'll get as we got with our full wave theory. However, this approximations break down very quickly if you go to dielectric waveguides where there's no metal involved, and if those dielectric waveguides are asymmetric. So, if you were studying about 50 years before, or if you pick up books which were written before 1980s, you'll see a lot of treatment given to how to calculate these waves, how to calculate the modal conditions based on these based on these reflections. However, uh, because this does not tell you the complete picture, this picture breaks down very quickly when you go to dielectric waveguides. Uh, the modern day books, the modern day people, and even me, we just use this for some physical understanding rather than for doing full computations. However, this is effectively the reason why we start seeing. So this is if you notice when I was showing you the modes of the TE, it looked like a guitar string. The first order mode was such that the electric field has to be zero at the boundaries, and then there is a single ohm. That's the first order mode of a guitar string. Why does the mode of a guitar string happen? Because you get the reflections, two reflections, right at the places where you're holding the guitar string. And only certain distributions are allowed after that. There is a superposition of those two reflections. There is constructive superposition or destructive superposition, and only certain distributions would be allowed. In order to now understand what does phase velocity means, Remember, this ray here is traveling again. We said that the material inside is some material mu epsilon. The rays inside are traveling at the speed of the material of the rays traveling at the speed of the material in there. If I was going to try to calculate what that angle is going to be and how that is going to be related to the propagation constant, well, effectively what I have here is I have a plane wave which is traveling in this direction, making some angle theta m to the normal, getting reflected off the bottom and coming back up. This wave here would be traveling with beta prime, the beta prime being the material propagation constant omega epsilon, the propagation constant in the dielectric material. We can break this part into two parts. We have a propagation constant in beta in the z direction, which is what we calculated for the mode. What we calculated for the mode was beta. So this is how it is propagating in z direction. This is what we calculated with wave analysis. And you can clearly see that this beta is going to be smaller than beta prime. This beta is going to be smaller than omega square root of mu epsilon, which is exactly what we had seen before. It was reduced by, in fact, like if you remember correctly, beta was omega square root of mu epsilon 1 minus omega c square by omega square. Square root of that, I believe. So we know that this beta is going to be less than that beta prime. And again, remember the phase velocity as we have defined it is omega by beta. So since beta is going to be less than beta prime, the apparent phase velocity is going to be larger than that for the material. So the apparent phase velocity is going to be much larger than that as compared to the material. This is if you have been to the beaches and you see waves coming at you from far off, and if those waves hit the beach at an angle, instead of coming right into the beach, if the waves are hitting the beach at an angle, next time if you go to a beach, I believe you have beautiful beaches around here. Next time go to the beach and observe that when the waves are hitting the beach at an angle, and if you observe the troughs or the crests, sitting on the beach like that, waves coming and hitting you at an angle, to you the troughs and the crests would seem to move faster if you were seeing at an angle as opposed to if you were seeing normally to the troughs and the crests. To you it would look like while this, so let's say if I was looking at the trough and the crest and I am, let me redraw that. I am sitting here and observing the troughs and the crests, and the troughs and the crests are going like that. You clearly would see that I would see this trough, and then I would suddenly see this trough very, very close by. So that is the phase. The phase is how the argument of the function is moving. So I would see when I'm at this place, I see this trough hitting me, and immediately behind it, even before this point has reached me, the because it's a wave coming at a plane wave, this trough comes and hits me, or this crest comes and hits me again. So it looks like to me as if the crests are hitting me at much faster speed than the actual motion which the medium allows me to do. Any questions on this? Right? Let's see if we can calculate the angle. We have said that we have beta prime, we have beta, which is the propagation constant in the z direction, which we have calculated, and we have another beta. If I was decomposing it, this would be in the y direction. Remember, beta square was omega square mu epsilon minus m pi by a square. If it's writing this form, this is beta square plus m pi by a square is omega square mu epsilon, and this is your beta prime square. It's telling me that I have a beta y which was of the type of m pi by a, and if I'm calling this angle to be theta m, this is equal to beta prime cos theta m. Just the projection of beta prime on the y-axis. So theta m is going to be cos inverse of beta y divided by beta prime, which is, sorry, cos inverse of beta y by beta prime, which if I now substitute, it will be cos inverse of m pi by a divided by beta prime, we said was omega square root of mu epsilon, and m pi by a 1 by mu epsilon is nothing but is the cutoff frequency. So this theta m angle would be cos inverse WCM by omega. And you notice from here that if my WCM is smaller, so for first order mode I would have WCM, which would be for TE1 mode I would have WCM at lower frequency. My angle again cos is uh, smaller the argument of cos, the larger the value is. So if this value is small, this theta m is going to be large. For small WCM, theta m is larger. So that's what I told you before, that the lower order terms, the smaller the the smaller the mode is, the smaller the value of m is, the more oblique angle it makes. Larger the value of m, the more acute angle it would make. So this would be, for example, m is equal to 1, this would be m is equal to 2. The angle theta m would become smaller as you go to higher order terms. It would look like as if you're bouncing between the uh, two plates much uh, at a much larger rate, as you go to higher order terms. Similarly now, if I was now going to look for what is the velocity of energy travel. Remember again, so far we have seen that Vp was Vp medium by 1 minus omega c square by omega square. So this was going at a much, so this Vp was greater than Vp medium. And again, Vp medium is given by 1 by square root of mu epsilon for that medium. If I go to this array analogy, I have wave traveling this way. This wave would travel with that of speed of the medium. But in principle, what I'm really interested in knowing is how does the energy travel in Z? I'm not really caring about how this bounces back and forth, but how does this energy travel in Z? How fast does this energy travel in Z? So all I have to do is I have Vp medium, so there is this energy which is traveling, or this wave which is traveling in this direction, but I'm interested in knowing how that wave would travel the energy forward. This is the component which I'm really interested in knowing, and this would be the component which would be the component which would basically tell me how the energy is going to flow. Again, if I look at theta m, that term over here, this component, this red component, is going to be Vp medium multiplied by sine theta m, just using the projections. And this component is called the group velocity Vg. So if I look at Vg, the group velocity Vg is going to be Vp medium sine of theta m, and I can write that as Vp medium 1 minus cos square theta m. I have already calculated what cos theta m was. So cos theta m was basically given by omega cm by omega. So cos theta m is omega cm by omega. So the group velocity, which is the velocity with which the energy is moving, is going to be Vp medium 1 minus omega cm square by omega square. So for parallel plate waveguide, a very unique thing comes out, and this happens for almost all metallic waveguides. Your phase velocity is happening at Vp medium 1 minus omega cm by omega square, and your group velocity is happening at Vp medium multiplied by 1 omega Cm square by omega square. And if you notice, this is less than 1 for omega greater than omega cutoff, and thus your Vg is less than Vp medium, and that is your statement. Information cannot travel faster than speed of light. Information is the energy being carried by the wave, not the phase of the wave. So information cannot travel faster than speed of light, at least in this classical domain. And also notice that if I multiply Vp by Vg, you just get Vp medium square. This is only true in metallic waveguides. For dielectric waveguides, this does not happen at all. This is only true when you have metal bounding the waves, when you are forcing the electric field to go to zero at the boundary. Any questions on this? So the reason that the wave's phase velocity looks larger than that of the medium itself is because there are two plane waves going at oblique incidences and hitting the metal and getting reflected off. And when you are measuring something at at an angle straight to that, it would look to you that the crests are going to move faster, and how fast the crest would move would depend upon the would depend upon the angle. The more the angle, acute angle you have, the more the crest would appear to move faster towards you. But the real energy, the energy and the information is going to be traveling slower because you're going through this long path instead of just taking a straight path through. And just by relativity, whatever the phase looks like by faster is how the energy is going to be slowed down to. It's going to be related by the same angle, theta. So the phase velocity for higher order modes, remember again, if I was looking at the phase velocity, this is Vp medium 1 minus omega Cm square by omega square. So if I'm operating at a specific omega, then for TE1 mode, if I was looking at the omega Cm for the first mode, omega cutoff for the first mode by omega, this value is going to be smaller than the value for omega Cm for the second mode by omega is going to be smaller than the value for the third mode by omega. This is for TE1, TE2, TE3. So this is always going to happen. for TE1, TE2, and T3, like the cutoff frequencies are, in fact, the cutoff frequency omega CM2 is nothing but twice the cutoff frequency for omega CM1. So it's telling you that the phase velocity for the first mode, this number is going to be closer to 1. So the phase velocity for the first mode is going to be smaller than the phase velocity for the second mode, is going to be smaller than the phase velocity for the third mode. And again, you can make the argument from the angle point of view too. Theta m for first mode is going to be larger than theta m for the second mode, is going to be larger than theta m for the third mode. So if you're coming at much acute angle uh, uh, to the uh, to the boundary, you are basically zigzagging a lot. So the effect, that relative effect you're going to get on the phase velocity is going to be larger. But in terms of group velocity, it's going to be the opposite. The group velocity for the first mode is going to be larger than the group velocity for the second mode, is going to be larger than the group velocity for the third mode. But all those values are going to be different. Each of that mode, each of that solution is carrying the information at its own speed. So if I allow three different horses to run through this waveguide, all those horses are going to take, they're going to be unique horses. All those horses are going to take their own time. Each is going to go at different speeds. The first horse, the first order horse, is going to go much faster than the second order horse, is going to go much faster than the third order mode. And as we will do rectangular waveguides and throw you questions on that time, you'll realize that when we do communication, most of the time, whether it is with rectangular waveguides or whether it is with metallic waveguides or dielectric waveguides like optical fiber, we want to design the waveguides such that only a single mode can exist inside, only a single solution exists inside, so that the waveguide is dimensions or for the frequency are below the cutoff frequency of the second order mode. And we'll do this questions later on. Any questions on this part? You have any questions? Or all right, let's go to the last topic then for this unit, and that is attenuation in different modes. So far, what we have assumed is that the conductors are perfect, which basically means that the conductivity, the sigma, the conductivity is infinite. However, there's nothing such exists. Conductors in reality would have some resistance in them. Now remember, we have these waveguides, and for the TE mode, we had seen that we have a solution which is Ex, we have a solution Hy, and we have a small component Hz. This component hz, if I was plotting this, if I was plotting this component, hz is parallel to the conductors. And remember again, hz had a variation of cost function. If you go back and look at the notes from yesterday, when you looked at hz, it had a variation of cost function. So if I was taking the first order mode, for example, hz amplitude was varying like that. Hz was maximum at the conducting boundary. The conducting boundary states that if you have a magnetic field which is parallel to a conductor, then there is going to be an induced current which is going to go perpendicular to that direction. So if I have a field which is coming parallel to the conductor Hz, I am going to start creating current which is going to go in the perpendicular plane, the x plane. So I'm going to create a current in the Jx plane. And if the conductor has some resistance, this current is going to see that resistance, it is going to see some Joule heating. And because it's going to see some Joule heating, I am going to lose energy. That heating is that the energy for that heating is going to come out of my wave. There's no other source of energy available to me. So it tells me that there is going to be loss due to the conductors. Also, this waveguides we have done are filled with a dielectric mu and epsilon. Let me change the color so you can see that. They're filled with a dielectric, and there can be loss in the dielectric too. Most of the waveguides have air as a dielectric. Which means mu is mu naught, epsilon is epsilon naught. So this loss due to the dielectric is generally very small. So we won't worry about it for the time being. So we are not going to worry about the loss within the for the time being. Now let's see. So I have two different modes we have said. So let's see what the conductor loss is. And before we do the maths, and the maths is pretty cumbersome here. It's pretty intense maths. So before we do the maths, let's think through the problem and let's see if we can make predictions of what the loss could be. Especially when the maths becomes cumbersome, it's always good to make the predictions to know that at the end, are you getting a right answer or not. So we have a TE mode and we have a TM mode. I want to physically think which will have higher loss and what will happen to the loss as frequency increases. Obviously, the loss below the cutoff frequency is going to be infinite. There's no propagation going through. So I'm only interested in thinking about it after the cutoff frequency. The loss I'm saying is coming due to the current being induced in the conductor and due to the finite conductivity or having the conductor having some resistance to it. For the TE mode, we know that the wave is traveling in z direction, so this is x and y. The current is being introduced by hz direction. So I have component Ex, a component Hy, and a component Hz. So for Te, loss is happening due to Hz component. That's the component which is parallel to the boundary, and that's the component which is going to start to create fields around, create current at that conductors. For TM mode, on the other hand, I have Hx, I have Ey, and I have Ez. It's the Hx component which is parallel to the conductor, to the two conductors, and thus it is the Hx component which is going to be creating the loss. Now, if you go back and look at the equations we had derived, and I'll probably throw you some questions tomorrow anyway to look at it numerically. What happens is the transverse components are always stronger than transverse components are stronger than the longitudinal ones. They have higher amplitude than the longitudinal ones. The loss in the TE mode is coming due to the longitudinal component of H field, whereas the loss in the TM mode is coming due to the transverse component of the H field. The transverse component of the H field is the one which is actually confining the electromagnetic field according to the Poynting vector. So I expect that the loss for TE is going to be smaller than loss for TM. The loss for the TE mode is going to be smaller, and it's going to be appreciably smaller as compared to the loss for the TM mode. And other thing you notice is if the angle we had talked about, the theta m angle, was cos inverse WCM by W. As frequency is increasing, as omega is increasing, theta m is decreasing, is increasing. As that frequency for a specific mode, if I keep on going to higher and higher frequencies, as the frequency is increasing, as this omega is increasing, this term is decreasing, and if the argument of a cos inverse function decreases, the angle is increasing. Cos 90 is 0, cos 0 is 1. So as the value is decreasing, the angle is approaching 90 degrees. So theta m is increasing. What it tells me is that when I go to different theta m's, so originally, let's say at one frequency, I have my angle this way, f1. At another frequency, which I'm going to larger term, the angle has increased. This is f2, such that f2 is greater than f1. One thing you notice is in terms of the ray diagram or in terms of the plane wave decomposition, you are making much more larger bounces and thus you're interacting with the metal a lot more when f1 is smaller than f2. So what I expect for TE mode is that as the frequency is going to increase, the loss is going to keep on decreasing. In other terms, you also know that as frequency is increasing, you have, as we had seen before, this was m pi by a, this was beta, this was beta prime. As the frequency is increasing, this term m pi by a term is decreasing. As frequency increases, m pi by a decreases. As that decreases, go back and look at your equations we derived yesterday. You will notice as m pi by a decreases, h z decreases. The component value of hz has m pi by a right in front of it. So as the frequency increases, that component strength keeps on decreasing. If I go to very, very large frequencies, the TE wave is almost behaving like a quasi-TEM wave. It only has an almost EX and an HY component. So what do I expect? So my postulates are, just by thinking through the problem, loss for TE is going to be greater than loss for TM, and loss for TE is going to keep on decreasing as frequency increases. These are my postulates. All right, let's do the maths. I'll probably put you to sleep for the next 20 minutes we have. Bear with me. There's no easy way around it. So we know we are looking for a loss term. So we are looking for a term where I'm looking for the field attenuating in z direction due to conductors. So basically, ideally I know E has to be related to some E minus alpha C. I'm putting the subscript C to just remind us that it is loss which is happening due to the conductors. not due to the geometry of the waveguide. I'm looking for calculating what this alpha c would be. Remember again from last year or last term, Poynting vector, which is the energy density vector, Poynting vector S average is given by half of real of E cross H star. So if the electric field is and H and E are related by the wave impedance theta. So if E is decaying by alpha c, the average power would decay by twice of alpha cz. You remember, average power would be proportional to magnitude of E square. So to calculate now, basically this term here is called the Beer-Lambert law. And the differential equation is basically that the average over z is going to go as some 2 alpha c p average. Whatever average power I started with. If I started with an average power of P average and I went a small distance delta Z, then basically P average after delta Z would be P average I started with exponential minus 2 alpha C delta Z. Taking the log of it, you can write this differential equation. So to calculate my alpha C easily, I can do the calculation of power lost per unit length divided by power transmitted. Power lost per unit length is the right hand side of that equation is 2 alpha c p average. Power transmitted is p average. So you can see this would be equal to 2 alpha c. You can see this is going to be equal to 2 alpha c. So to calculate alpha c, what I have to do is calculate half of P loss, how much power is going to be lost, divided by P average. P average comes from Poynting vector and integration of it. P loss comes from your circuit theory. P loss comes from the fact that you have current going through a specific resistance within the conductor. How much loss would I see here? P loss comes from circuit theory. So let's consider the TE wave. So for TE wave, We had said that basically if I was looking at my surface current in the conductor, surface current density, that is given by my the boundary condition we have, normal to the boundary cross H, which is just a unit vector. So I know my J surface normal is going to be equal to the magnitude of my HZ field. From yesterday's derivations, the amplitude of Hz was m pi by A, the magnitude we had, omega mu A. That's what I was telling you, that the Hz component has m pi by A hidden within it. And as the frequency is increasing, m pi by A is decreasing, and thus my Hz component is going to keep on decreasing. So my surface current density, which is going to be magnitude of Hz, is going to be m pi by A omega mu A. And if I calculate P loss, let's assume we have a width of B on the conductor, and we are traveling 1 meter in Z direction. So we are going to calculate the loss per unit length of our waveguide. Going back to your circuit now, if the resistance is Rs, the P loss is going to be integral of the surface over the width, surface current over the width, integral of over the length, 1 meter, and this is going to be half of magnitude of J, the current density square, Rs, and we are integrating it in the Y and the Z direction. That is going to be my P loss. But my total P loss, I have two conductors. Whatever is the current in the bottom, there is an equal and opposite current in the top direction. If the current in one direction is flowing in Y direction, the current in plus X direction, the current on the top conductor is going to flow in the minus X direction. So I am going to get a factor of 2. This factor of 2 is coming from two conductors, and this equation is coming from your either your E&M course you should have done in first year electromagnetic or basic circuit course. So if I substitute these values, my loss becomes just integrate J surface normal, if you notice, is all constants. So it's a very simple integration. It would be B m square pi square A square omega mu naught by 2 sigma, sigma being the current density, omega square mu square by A square. And basically, to get the sigma term, I am using the fact that the RS term, and this is from your course last time, Rs is omega mu naught by 2 sigma for a conductor. You must have done this when you did the electromagnetic wave. So that is the loss term which I get. Now I have to calculate how much average power my wave is carrying. The S average, we know, and all I'm interested in is the magnitude, is half of real of E cross H star, and this would be uh, this would basically be given as, in terms of magnitude, would be half of EY HX star. Substituting the terms we had gotten yesterday, this would be beta A square 2 omega mu sine square m pi by a y. So I'm just substituting the terms from yesterday. And the P average is going to be integrating. So I have this waveguide. The average power is being stored here. So I have to integrate. So I'm looking at how much is the average power stored in this cross section. This being B, this being A. So I have to go from y is equal to 0 to A, x is equal to 0 to B, and I integrate my S average over dx dy. That becomes 0 to A, 0 to B. Substitute the terms, I get beta A square 2 omega mu sine square m pi by a y dx dy. These are just constants. This is a sine square function with respect to dy. If you remember your Fourier transforms well, the integral of that is always going to be the if it goes over at least one period, is going to be the difference between the subscripts divided by 2. So this just becomes beta a square 2 omega mu b multiplied by, sorry, beta a square, capital A square b multiplied by a by 2, or it would be beta a square ab by 4 omega mu. So if I'll put these notes online so you can see these equations. But if I look at my alpha TE and I put the value of P average by P loss by 2P average, the result I get is 2RS omega C by omega square, eta A 1 minus omega C by omega square. Just substituting the terms in, nothing much, where eta is Ex by Hy. Ex by Hy, yeah. The magnitudes of those. Notice here, what do you see? You see if Rs doesn't change, which is not necessarily fully true, if Rs does not change, then as I go to larger values of omega, this term drops down very, very quickly. Though this term is also dropping down, this term is becoming, and then this term is becoming larger too. So because of that, as omega c goes up from the term, it becomes pretty, the loss starts to become very low. So if I was plotting this loss for a mode, Let's say this is omega C1 for the first order cutoff. When I am at omega is equal to omega C, I would have this term would be infinity, so the loss would be very, very large. As I go further away, the loss would drop and would keep on dropping as the frequency is decreasing. We're running out of time, so I'll just give you alpha Tm. Alpha Tm, you can do the same mathematical exercise. Alpha Tm turns out to be 2Rs by eta A square root of 1 minus WCm by W square. If I was going to plot that term, it's not apparent how it really goes through that. But if I was plotting that term, what you would notice is, yes, you start with infinity, but then you go down to a minima, and then after that, the Tm loss starts increasing. So this is Te loss, this is Tm loss. Te loss keeps on decreasing as you go to larger frequencies. Tm loss decreases and then it starts to really increase. This minima for the mode happens at slightly smaller than 2 times omega C1. It depends on the waveguide, but it happens at a value which is just slightly smaller than twice the resonance frequency. So because of this higher loss of the Tm, nobody really wants to use the Tm modes. And even if these modes are excited, they by the time they travel through the waveguides, most of their energy would be lost. You would not get that energy back. So normal operation of these waveguides happen in the TE mode because of its lower loss. All right, I guess the time is up. Uh, do you have any questions, Jaya? Or